are you doing?
All the way across campus.
Oh, okay. I know how that
I had a new lab today, so.
Oh, you had a lab?
Yeah.
Oh, okay. There is no power. Good afternoon, guys. To everyone on Zoom, if you can just give me a thumbs up that the mic is all working. And we're gonna get, thank you so much. We're gonna get started here in just a minute. Let me go ahead and share my screen. What says-
I was going to do that, after that, there's some.
Okay, let's go ahead and begin. Good afternoon, everyone. To all you guys that are here and the ones on Zoom. So today, just to speak course logistics before we dive into our chapter. For one of the TAs, his office hours is updated. So his office hours are Thursdays and Fridays from 9 to 10. And that's the same way you join the lectures. You can join through here. Basically go to the Zoom section and click join. The other TA hasn't had web course access, so as soon as he gets web course access, I'll update that as well. For our modules today, we will finish chapter 1. So today is the last section of chapter 1. And next week we'll start on the application layer. So I have released the exercise for the circuit switching and a video to explain the problems that we went over. So for now, let's go ahead and dive to our chapter. Okay, great. So as to state this every lecture, the class is recorded and a portion of the slides is coming from this link, which is the book, the main book for this class that we talk about, which is a top-down approach to networking. So the lecture objectives for today's lecture is we want to summarize how data is encapsulated across the protocol layers using the internet and the OSI reference model. We spoke in the last lecture about the OSI model briefly and gave an idea of what it is. Most of you guys already know about it, but today we will go in detail. We'll identify and explain the main types of delays. As we said, whenever we have devices that are sending packets to the router has a buffer, and there could be a lot of things that can happen with that, such as delays, packets being lost. So we will talk about the different types of delays and how they contribute to packet loss. We'll explain the throughput and the performance and factors in networking, including the bottlenecks and the shared link capacity. We spoke about the link, which is the various physical links that we would have, and it's the transmission link that would transfer the packets to the receiver from the client or from the server, from the client to the server, vice versa. So when we talk about explain the throughput and performance and factors, we're talking about the whole process, and I'll explain when we get to that. We'll also recognize common network security threats. This is mostly coming from chapter 8, but we will have to cover and give an overview about it. We'll talk about denial of service, packet sniffing, IP spoofing, along with basic defense strategies. And then finally, we'll discuss the history and evolution of internet, from when they started and to how they are now. We spoke about the structure in the last lecture and how the structure of the internet is now. And I'll give a brief introduction to Wireshark for today, just what is Wireshark and what it does, and then we will conclude. Okay, so here's the roadmap. So far we covered from point 1 to 3. We talked about what the internet is. We talked about the network edges, which is end system access networks and links. We talked about network core, which is in the last lecture. We talked about packet switching, how it's different from circuit switching in terms of allocation, network structure. We also talked about that. So today we will continue on delay, loss, throughput, and networks. And then we will also talk about protocol layers, service models, network under attacks, and finally the history. So back to this slide. This is just some slides I recap from last slide. So we talked about packet delay and how that could happen and how the loss occurs. So last lecture we said that there's multiple devices that are sending data, and if we look at the OSI model, this is getting sent in the network layer, which can turn into packets. So we have two devices, two different transmission links. One could be higher than the other. When the packets get sent here to the router has a buffer. So with the router, when the buffer gets overflown with the packets and the data, we have packets that get lost. If there is available space in the buffer, then the packets will get stored, and they will, once they get stored and they get completed, they get sent to the next router. So all the lines that we see here are the transmission links that are connected from devices, routers to routers, or switches to routers. So it could be any of that. So packets queue and router buffers waiting for turn to transmission. Queue length grows when the arrival link temporarily exceeds the output link capacity. And packet loss occurs when memory hold when queued packets get filled up. So with the type of delays, we know that the packets don't travel, and it travels, it doesn't fly, sorry. And we have this figure here. Right now you can see that there is no delays. In the next slides, we'll cover the 4 main delays, and which are processing delay, queuing, transmission, and propagation. So the first type of delay, also known as the nodal processing, it's the time that a router takes to examine the packet's header and decide where to forward it. We know with the OSI model, it has various layers, and each one adds a header. Basically, it adds a remark of what happened to the data. So we know that data starts as a payload or raw data, and then in the next layer, it becomes a datagram or segments, depending on which protocol we use. And then after it gets past the protocol, it becomes a packet. And then after it becomes a packet, it becomes a frame in the link layer. Then it goes to the physical layer that gets transmitted via physical links. So when we receive the data here for the packets, this is the time that a router takes to examine the packet header and decide to where to forward it. Okay, I'm getting a packet. I want to know where I should forward it to. You can think of this as an analogy of the postal office. When they receive mail, they get a bunch of mails and they sort it out. Okay, this is going maybe to Oviedo, this is going to Seminole, whatever, and then that's the time that it takes. It's usually very small, milliseconds when we're speaking in terms of packets. And in terms of network, with the technology that we have now, it's very efficient. We're not feeling this, but we must discuss it from a theoretical point of view and a network model point of view as well. So it also includes error check-in bits and checks for dropped packets, which we'll do a short activity today with the trace route. Queuing delay. This is the time a packet spends waiting in the buffer. You know, when the packets get sent, there's a buffer in the router, it stays there, and then after the buffer is filled, packets get dropped and lost. So it depends on the traffic load. It can be very small or very large. If the queue is filled, packets are going to get dropped. Transmission and propagation delay. Okay, so we have the transmission delay that we talked about. It's time that pushes all the bits of the packet onto the link. From the link to the router to the other link that's transferring to the router. And the formula for that is we use the L, which are the bits over time. And the propagation delay is, you can think of it as how long it takes the packet to move through the transmission link. So think of it as a car moving during traffic. This is the time that we're calculating. So the time for the signal to travel across the link, and that depends on the distance in the medium. And we spoke about different physical cables, how each one is powerful than the other, cable, DSL, fiber optic, and then we have the hybrid, and there's various ones. Now let me put this one down. This is better for you guys to see. So we spoke a little bit from theoretical. We'll dive a little bit hands-on of the delay, real internet delays and routes. And what do real internet delays look like? So in class, like the previous lecture and today's lecture, we spoke about the 4 delays. But in the real internet, delays and packet loss can be observed using tools like traceroute. So this is a tool to mess with today and see how it looks. So what this tool is basically, it helps us measure the delays that are happening hop by hop. So maybe from router to router, device to device, from IP address to another, along the path from a source computer to a destination computer. So if you can just focus on the figure here, we have 2 devices. We have this one and that one, and we are sending that. These are the packets. When they get sent to different routers, for us to calculate the time of when the packet leaves to the first destination and comes back, we send 3 probes, and 3 probes are just basically AKA packets. So we send 3 packets to the first router and it sends 3 back. You might ask why. Does anyone know why we send 3 out instead of 1, 2, 4, or 5? Okay. So the reason we do that is just to make sure there is no inconsistencies, because usually it's with the time, it could vary. So if we send 1 out and that one gets sent back, or 2, so 3 is like you can say an optimal number that we can use to say that, okay, we send 3 out, we can take the average of those 3 times and say, hey, this is the actual time. Because the time difference between the 3, it won't be a big of a difference, but it'll be different in milliseconds. I thought it uses ISMP to TO. You are meaning with the trace route, or how exactly? Because we have an example in the next slide that we'll talk about how tracing that would happen. So it sends 3 packets to the router, and the router returns a response. The sender measures the delay. Yes, okay, yeah, we'll dive into it in a little bit. So yes, the sender measures the delay as time from the probe was sent until the reply comes back. During the 3 times, it helps us average out random inconsistencies. So this is the main idea. We go to the next slide. Here we have an example, okay? And this is a trace route being done from this website to this website. And there's a bunch of things that we have to realize here. The first thing is the number of hops. We have here in this example, we have 19. So from the 1st to the 19th, those are how many hops it will take from the source to the destination, okay? And then here, each router gets 3 probes that we talked about, and times are shown in round trip milliseconds. So, and I said that the time is not going to be a huge difference, 1 millisecond, 1, and then 2. It's not a lot. So here we have 3 delay measurements, helps confirm the delay consistency. And here we have the time, there's a jump from here to here. Does anyone know why there's a huge jump? It relates to the structure of internet and devices. So in the last lecture, we spoke about when we speak about structures, it starts basically with devices, laptops, various devices that are connected to hubs, switches, routers, and these are connected across a regional, and those regionals are connected to global ISPs and then the internet exchange points. So when we are tracing something that's maybe overseas, there might be a big jump in terms of the milliseconds, where we have here a transocean link. That's going through the ocean. So there's a higher delay, more physical distance. Also, you might realize that in some hubs, there is a domain name system, and the DNS, we can think of it as our phone. We have a bunch of contacts in our phone, and they have the number saved and the name saved. But whenever we receive a new call, the call does not have a name. So this is basically the idea of DNS. So some routers, some hops just have an IP address. They do not have a domain name system. And here we have some hops that show 3 stars. That means packet may be dropped or filtered. And traceroute, what it does is just a tracing tool, and it does its best it can to trace the route. It doesn't mean the packets don't get moved forward. They do, but we don't really know the detailed information. Okay. So this is what we're gonna do now. For the people, for the students to have Mac and Windows, we're just gonna run a simple trace route for a domain for any destination that we want. So for me, I tried Amazon yesterday, and I'm gonna try it here on the PC that we have. And so just in case. I'm gonna try to leave this out so that you can see it. Let me get to the scene. And here I have my trace routes for Amazon. If we just type in trace RT and then we type in Amazon.com to me. Okay, this is equivalent to what happens there. So it starts from hop 1. It tells us our current IP address, and it tells us that's from currently here from the source to the destination. It's going to be over a maximum of 30 hops, and it's going to take some time to calculate, but here's what we can see in the last picture that we talked about. The first thing is there's 3 probes, and there's 3 different times for each probe. Although here it does not show the domains and the IP addresses of the hops, which is weird because when I tried it on my local PC, it actually doesn't show it either, but in the example it does. So that's kind of weird. But yeah, one of the hops that we see here is stars was timed out, so it couldn't retrieve the information for that. We'll just let it continue here, and you guys can try it on your side. You can put any website that you'd like to trace. It doesn't have to be Amazon specifically. Yes.
So since it's showing them all like sequential, does that mean it's going to each hop coming back, next hop coming back, and going that way rather than going all the way like forward and then all the way back?
Like from 1 to 20 and coming back?
Yeah.
No, it goes through each hop. Each hop.
So like from 1 to 2 back to 1,
Yes.
3, 1, 4, 1.
Yeah, in terms of the time, yeah.
Okay.
Yeah, my knowledge of it is that it sets a time to live, it sends a time to live packet over 1, and the first router it reaches, it returns that, then it changes it to 2, then it goes to the next one, and then it keeps going there until it reaches its destination.
Mm-hmm. I brought my personal because I didn't know if the UCF laptops allowed us to do something like that. I know for when we get to the application layer, I might have to use my personal PC. And we'll use some applications like Mobile Extern. If anyone heard of that before, yeah. But this is the idea of it. We will let it sit and we will continue, but this is the idea of traceroute and how we can calculate the delays that are happening from the source to the destination. And it usually ends around 20 hops. It does not take the maximum of 30. Okay, now we'll continue. So, okay, we'll speak about packet loss here. So AKA the buffer. We said that each router has a buffer, and then when the buffer overflows, the packets get lost. So the lost packet may be transmitted by previous node by source and system or not at all. Okay. And now we will talk about throughput, which is a little bit different from the delays that we've been counting. We counted the delay that would happen from one router to another till it gets to the destination. But throughput is, you can think of it like, to give you an analogy, we have a factory, right? And we have a customer, which is the receiver. and the factory could produce anything. For example, it could be donuts. This is the time we're trying to calculate that when the products get done at the factory and when it touches the customer, the receiver. And there is different, you could say, blocks that it goes with. So for the factory analogy, there's roads. There's narrow roads. There's roads that have congestion, a variation of roads. So these are the network pipes. So basically, throughput is the receiver actual rate of delivery, not just through the theoretical link speed that we talked about. So instantaneous is the rate at a specific moment. The average is the rate over a long period of time. And the bottleneck link is the nearest pipe that decides end-to-end throughput. So here for the visualization, the bottleneck link is this one right here. So we must comply with whatever it could do here, meaning that from the server, when it sends packets to the router, it sends it at a specific speed. So we have to calculate that and keep that in mind. Maybe when it gets from the next router and it goes to the client, the throughput is big, so it can handle more. That means it's going to get there quicker. But back to our analogy, if the one road is very narrow, all trucks must slow down there, even if the other roads are wide. Okay. So here it just gives us two different examples. And the last one that we've seen a bottleneck from the server to the router. Here it could be different. We have the first one from the server to the router, and from the router to the PC gets bigger, and then vice versa. So this could what happens. So it's the bottleneck link is the link on the end path that constrains end-to-end throughput. And here's a scenario. When we spoke about structures of internet, we said that it starts out with devices, it grows out to multiple devices, multiple hubs, multiple ISPs, regional, and it gets bigger. So the same idea here, the bottleneck gets shared from multiple devices. So a link with capacity R is shared among the multiple users that are the servers that are sending packets or data to the receiver. So if there are one or few users, each can get a high throughput, close to R. If there are many users, the link capacity is divided, each gets less. So think of it as traffic. If there won't be a lot of traffic if there's not a lot of cars, and then vice versa. So end-to-end throughput depends on both link capacity and the active users that are there. And we talked about that in the last lecture with packet switching, circuit switching. So for the question here, when multiple users, for you guys, share a single link capacity R, is this an example of circuit switching or packet switching? Packet switching, yes. So because we said with circuit switching, it's reserved, whether it's done by times or done by frames, number of allocated users. So when the circuit switching, when a server channel is intended only for that special user. So if he uses it only once, it goes on idle and it stays reserved for them only. Okay, next we'll speak about protocol layers and the service models. So protocol layers and reference models. We said that in the last lecture, networks are complex with many pieces. If we think about it in a big point of view, yes, it is very complex, but when we go down to the nitty-gritty, it gets easier. And that's usually with every problem. With a complex problem, we have various tools that from the mathematical department, it could be CS related, and these tools are set to help us break down the complex problem and maybe make it complicated into simple terms, depending on what we need. So it's complex because of various things. We have hosts, we have routers, we have links of various media, application, protocols, hardware, software. So the question now here, is there a hope of organizing the structure of a network? And if there is, how do we go about doing that? Anyone has an idea? They didn't say anything, but basically we have to have a structure to everything because we need to know with networking, we need to know if something happens, who is responsible for that. And the OSI model is basically our guideline, our blueprint for that. We'll speak more about it today. So before we get to the OSI model, I have an analogy about airplane routing. So end-to-end transfer of person plus the luggage. Usually what you do is you would plan your trip, right? And say, for example, you're going to California. So first thing you do is you do your ticket purchase. You purchase your tickets. That's being done through a special department. You might book it online in the airport. The baggage check is responsible for your bag. For your bags, they weight the bags, they give you a price for them, and you're good to go. At the gates, they load your bags in the airplane. And then the runaway takeoff takes off the plane, and then the airplane routing is from one destination to another. That's usually going to be physical, which is the airplane takes you from Florida to California, or from the destination that you're going to that you want to get to. So, and then the same steps get repeated here again. Land, airplane routing, you get to your route, it lands, you get the gates get unloaded, you grab your luggage, and you take your ticket. Complaint is just like a funny thing I would say, but the main thing is that if something happens with your ticket, you're not going to go to the gates department and tell them about it. They're only responsible for your ticket purchase. So your ticket purchase is only responsible for your ticket. So if anything happens, we go back to them. The same thing with the OSI model. We have our application, and it goes down to the data link layer. If there's any problem, it's very efficient to know, hey, this is the problem, and we go directly into it. Think of it like a workplace that has 7 departments. Each department is responsible for something. Anything happens, we go to that specific department. So it's a series of steps that involve many services. And these services, depending on how you're taking it from, if you're flying, or the same steps get repeated again, whether from a top-down approach or from a bottom to a top. Okay. Now, so we said that each layer implements a service. The ticket is over ticket service. The baggage is over baggage service. The gates, they're responsible of the gate service. The runaway takeoff is a service for the landing, and the airplane routing is the routing service via its own internal layer actions, and relying on services provided by layer below. Okay. Anyone, what do you guys, outside from the class, what do you think about the current flying system that we have? Is it very efficient, or there's some things that can be improved?
It's pretty efficient.
It's good. I think they do a pretty good.
Depends on the airline.
What is your favorite to fly with?
Well, I like American Airlines,
Okay,
but I don't like spending money, so I'll pick Southwest.
okay. But I heard that Southwest ranks higher than American or below?
Not below.
Oh,
Trust
below.
me, because I just looked at the price for December.
Okay, I see.
I just looked at it yesterday.
Yeah, so when it comes to flying, it's just depending on your cost and what you're gonna do.
Luggage is included, so.
Luggage is included,
Yeah.
yeah, exactly. So there's a lot of factors. So why there's a layering system? It's an approach / a way of design that we can discuss the complex systems. I think we have, yeah, this. So it's a structure that allows identification and relationship of the system of the pieces. It's a layered reference model for discussion, modularization, easy for maintenance for people that work in IT and take care of the system maintenance. Change in each layer service implementation, transparent to the rest of the system. So changing gate procedure does not affect your the rest of your flight, or affects the rest of the system. Okay, so we spoke about the OSI model, and this is just an overview. You might realize some layers, like the presentation, the session layer, is not really network related. You can consider client, presentation, and session is more of like end user and deals with the operating system with the client. But the client is, the application is very important for the client. We here as users, we deal with the applications, and we have various protocols. We set that for each specific layer. The transport processes data transfer using TCP and UDP. And now the question is, when does it become segments? And when does it become datagrams? With which protocol layer? So, do you want to see? No. Okay, so it becomes with UDP it becomes datagrams, and TCP it becomes segments. And we know that with TCP, it acknowledges the data it's got sent. Think of it like an email. An email gets sent and you get a reply. UDP just sends out the data. It does not acknowledge that the data has been received to the sender or not. So the network, we said that routing of datagrams from source to destination, and it adds and it does that with the IP, the routing protocols. And with the routing, it does two things. It forwards the data and it finds the best route for the data that is very efficient and the quickest way possible. The link is the link also adds a header. It adds a header and a tailer, which is the MAC address, and that's the data that transfers between network elements. And then we have the link and the physical. You can think of those that go hand to hand. We connect through Ethernet and wireless. It's wireless. It's via access points, and the physical transfer the bits that we understand as computer zeros and ones onto the wire. So here's the idea of encapsulation, and through the OSI model, we have a sending computer and a receiving computer, and the protocol of the network model in this example is peer-to-peer. So we have the application. It starts with the data. This is the original data that we see, and the transport layer it becomes segment. And that depends on which one we use. Here it's a segment because based on this image, it uses TCP. Okay. And the network layer adds a packet header. This basically adds the source IP and destination IP. And then when it gets to the network, yes, it adds the packet header, the IP of the source and the receiver. The data link adds a frame header and a frame trailer. It's the MAC address of the current device and the receiver device. And then it goes to the physical, which are the bits. And it also gets transferred to physical and repeats the same process going up. So has anyone messed with those before? Where did they origin from? I believe Russian, yeah, Russian. So I read about this yesterday, and the idea of encapsulation does not come from the DOL, but it's a good analogy. And basically, if you're not familiar with these, basically a toy that there's something at the bottom, but you have to open various layers to get to it. So this is the idea of encapsulation. You have a message in the application layer, it becomes a segment or a datagram depending on the protocol that you use, and then it becomes a frame, and then it gets sent out, and the process gets repeated. And here's an idea. So with that goes it goes in reference with the DOL. The message, which is M, this is the payload or the data, goes down to the transports. It becomes a segment. A network becomes as a datagram or a frame. With the link, it becomes a frame. Then it gets sent out to the physical. Then this is the destination. It connects physical to physical. It connects together, and then the same process get repeated again. And then you can see that the original message, the figure of it becomes like that because this is the idea of encapsulation. It goes down, and then when it goes up, you receive what the original message is. So end to end, basically another example here. What I want to focus is ideally on the switches and the router. Can anyone tell me why the switch doesn't go through the network layer here? And then we have the router, it goes to the network. So the main idea is we said that switches forwards the data. So it's not like a router. The router needs the IP address of the sender and the receiver. So it works directly with the network layer. The switch works with the MAC addresses. It forwards based on the MAC address. So it only needs the link. We know that the link layer adds a header and a tailor. This is the MAC address basically. And then here's just an idea of what happens from a source to destination. It goes down, and then when it gets to destination, it goes up, in comparison to the last figure. So now we talk about network security and securities under attack. That's right now. Yes, switches operate using MAC addresses and versus routers use the IP addresses. That's correct. So networks under security, this is coming mainly from chapter 8, but we'll give an overview of it today. So when the internet originally started, there wasn't much security in mind. And the idea that they had no security. And originally the vision of it was a group of mutual trusting users attached to a transport network. And to give you an analogy of that, this is basically in terms of social relationships. We have each one of us, we have strong ties and we have weak ties, basically. Your strong ties, you can rely on them and you can trust them. They're very close to you. These could be maybe your best friend, close families, uncles, aunts, it could be anything. And then your weak ties are people that you don't know. So the vision of these guys, I think that they had a mutual trusting, but that's not the idea and how we have. So okay, the early internet, ARPANET, it was built for research and for universities that they would transfer information over. And they thought that there was no concern for hackers or data theft or malicious use. But obviously now in today's world, we see there's a lot of malicious intent and there's various attacks with networking. One of them we talked about is denial of service. We will talk about it today as well. So we need to think about how bad guys can attack the computer networks and how can we defend? What are the defense protocols? We know when there's an attack, there's most likely going to be a way to defend against it. So we need to design architectures that are immune to attacks. Can anyone give me any architectures that would that are immune to attacks or that would fight against the attacks that are getting happen? It could be a tool that's CS related. I will speak about it in the next slides, but I just wanted to pick your brains and see. We can use a lot of tools, and one of them, we can build a model. And the model has an input of features, and those features are related to how the attack works. When we understand the feature of the attacks and how it happens, and we visualize it, we can defend against it. So I was pulling these up, and I wanted to bring real world case scenarios that had happened from a security attack. And attacks are attempts by an adversary to cause damage to valuable assets through exploring those vulnerabilities. So here's some that had happened. So WannaCry ransomware attack in 2017 affected over 200 computers worldwide. We also have the Equifax data breaches, and there's a lot of data breaches that we heard about recently. I think
Especially recently, most hackers now, they're attacking your data.
Mhm.
And for instance, if you have like, let's say T-Mobile or whatever, and T-Mobile decides to leak your information,
Mhm.
the highest bidder end up buying your information, and then that's where you get all these malicious phone calls, texts,
okay.
and all this good stuff. Yeah.
Do you guys get the ones with your mail has arrived or your
Yeah.
mail is somewhere?
Yeah.
Okay.
Just to see if you end up clicking on it.
And do you guys usually get malicious emails as to phishing, or rarely? Not a lot.
Well,
It's usually texts.
Texts.
Yeah.
Like I just use Google Mail, I think it's done pretty good at filtering out spam.
yeah, they can filter it out. Yeah, big,
Really?
big time.
I mean, what can you use in this case, though?
Yeah, it's try to minimize it as much as possible, but
Have any of you guys fell for something like that? That you got a text message or an email?
No, but I know plenty of people who have.
yeah, right.
Yeah. Actually, this is not like an attack, but there was an attack that was recently out where you get a text and it's from your friend. And he says, "Hey, I'm at the airport and I'm stuck and I need something." And yeah,
They were one of those.
yeah, and then you end up sending your money. But anyway, and then we have Equifax, and then the data breach that happened in 2017 with SolarWinds allowed hackers to spy on private and public organizations from once undetected. So what do the attackers usually seek? And it could be a lot of things. It could be theft, sabotage, destruction, espionage, tamper, and among many others that could be the main motivation or motive for them. So security attacks we spoke in the real world. This is an example from a mobile application. So just if you look at the figure here, we have a mobile app. And usually when you download the application, you have to accept the agreement for the privacy and for the permission. And trust me, do any of you guys read it?
I do.
You do?
That's why I minimize as much apps as possible on my phone.
You do?
Don't, even the updates, I even wait.
So you're saying you read that
I
3-page
read,
thing?
I look here, I
Okay.
like reading.
Okay,
I don't do anything. I just go to the gym,
okay,
home, school.
okay. And now, I think now there's a feature with certain apps, we can control what access we give it to, right?
Yeah.
Like the camera and the media.
Yeah.
But for the users that are not aware, they usually accept. So, and then permissions are requested by the app from the user. And the user usually accepts, so it grants them the permission. One permission that this is related to my research and one of the projects of my dissertation was on this. One of the permissions that gets requested is access my location. So it has access to your location. And if you go back, you can see it's a flashlight app. You do not need the location for a flashlight app. So it becomes a surveillance risk. So Android permission, regulate app access to location, storage, camera, microphone, network for privacy and security. Improper permissions can result in data leaks, indirect access, and privacy violations. Yes. Is mostly of you guys here Android users or iPhone? Android, you're using Android? Has anyone messed with the new, the one that folds? I think it's called, the, I think, who's the supplier of that? It's the one that expands like to two screens. Yeah, anyways, I mean, it has, I feel like in my opinion, Android comes out with a lot of nice features.
Yeah, nice features, but they're prone to.
Well, I think it's probably, I think Google Play app is probably bigger,
Okay.
even though it's security risk, I mean.
Did anyone switch? Did anyone had one before and
Yeah,
switched it?
Like when Google first came out with their first phones, I did, but then I switched.
And
It's been years.
ever
I've
since?
been with it. Man.
Yeah, there's so much more customization with Android, somehow it's your fault.
Exactly.
Okay. Do you guys think nowadays phones prices are overpricey or
Yeah,
Yeah.
you pay what?
Yes.
because they basically do all the same things and you're just paying just for.
They're smashing.
Yeah.
New battery, new
Still
camera.
14, I'm not even updating no point. That's gonna $50.
Yeah, like I think,
It's crazy.
yeah.
It used to be like you could barely get over eight.
Mhm. Yeah, I think I have the 16 and the only feature they have, I mean, this is the 16. The only feature they have from the 15 is they added the button on the side.
Yeah.
And you can zoom in and zoom out with it.
And the only difference is like the processing chip, you probably have to like.
And usually my dad is very strict when it comes to upgrading. Like he says, oh, it's a waste of money. Use your old phone. You don't
If you
need
know what
it.
to look for, yeah.
Yes. Okay. So when we go back to the type of attacks, denial of service, attackers may use resources, server bandwidth, to send a lot of traffic to the server that more than it can handle, because we know that it has a buffer. So that attacks flood a server with many requests. The service gets overloaded and cannot respond to the real users. Legitimate users are denied service website and it goes down. And maybe we have seen something like that in our personal use. And then also we have here is packet interception, aka packet sniffing. It's a broadcast media shared to the Ethernet and wireless. And what happens is that network interferes and reads all the packets, including passwords that are passing by from the server to the router to the device. And here's the idea of Wireshark that I'll speak at the end of the lecture just briefly about, and we will have an assignment with using Wireshark. IP spoofing, injection of packets with false source address. And the analogy to think of that before we get into it is it's like writing someone else's return address on an envelope. The letter looks like it came from the from them, but it's actually coming from you. So attackers forge the source IP address in a packet and makes it look like the packet came from a trusted source, not the attacker. And then it's used to trick the receiver into trusting the malicious traffic. Okay. Has anyone heard of the CIA triad? Yeah. Okay. And we can think of this as like our blueprint in terms of security and being secured against systems. So to secure digital system, we focus on 3 primary goals, and that's what the CIA stands for. First thing is confidentiality. We want to make sure that access is restricted to only authorized users. So here at UCF, you're an authorized user because you're a student, so you only have authorized access to the computers here. Also with confidentiality is a lot of students can have access, but we have different roles. So we have to set permissions for each role and what they can do. To authorized users, we want to make sure that those who are only can mess with the data is only authorized. It's only authorized for them. And availability, we want to make sure that it's all accessible by the authorized users and when needed. So a lot more of the security talks that we talk about will be in chapter 8, but this is just to give you an idea. Yeah, that we have here as well. The old one that we had at UCF, the Duo app, was way better than the one we have now, in my opinion, because I log in 3 times into Zoom and to web courses, and I get those to my phone. So list of defenses. So basically what defenses are strategies that counter the attacks to specific actions. And we have an idea of what to do with the strategy. We identify a compromised machine, we remove the malicious code, we patch the system and remove a vulnerability. We also make sure we want to report that and note it in case if it happens again, or we have different employees that would work, they can read that, okay? So a good defense system isn't one solution. It's a layer of protection that are working together. We have the threats, and you can think of this going down to when we have the threats, we want to make our system resilient. So we go through prevention, respond, and recovery. And preventions, we can use firewalls, secure design, access controls. For detection, we can use ML and natural language processing for detection model. And one research project that we worked on is classifying Android application and to see if they're malicious or not. So we grabbed a bunch of applications from the Google Play Store, and it could be from different developers, it could be from different regions. Anyways, we collected a bunch of applications and we had a good recent set of applications. Then we extracted the features of each application, the static artifacts and the metadata features, like we scraped those mainly from the Play Store. And then we use NLP and machine learning model, and there's various ones that we have. And we would feed the features into it, and we would test the model, and we would play with its parameters to get it to an optimal result. Okay, and then for the response, instead of response plans, malware removal, recovery, backups, patching system, configurations. When we speak about backups, maybe clouds, anything of that sort. Now, I'll go over these slides very quickly. It's the history of how networks started and where we are now. So when we talk about the history of networks, it breaks down to 4 main phases. And when you read about it, there you might break it down to multiple phases. So here is just a quick overview. So from the 1960s to 70s, we talked about AR PANET which is the packet switching. This is the beginning with to exchange information between universities. In the 80s, TCP/IP protocols came out, expansion to universities and labs. 90s to 2000, commercialization, the web, massive adoption, and now from 2005 to present has a very expansion with mobile, cloud, IoT devices, and internet being everywhere now. So the beginning, internet started for research plus military use in 1969. Introduced the idea of packet switching that we spoke about, an efficient way to send data. Early protocols, NCP, first host to host, then email in 1972, but with small scale at the time, only a handful of connected devices, aka nodes. Growth of networking, transition to the 83s. We came out with various protocols like the TCP and IP, foundation of the internet today. New protocols came out, DNS, FTP, SMTP, that we will cover in our next chapters, and networks expanded beyond research, beyond universities and labs, and beyond the main idea that it started with. By the late 80s, 1980s, 10 of thousand of hosts are worldwide. As we make our way down from the 1990s to 2000s, the web invented HTML, HTTP browsers like Mosaic and Netscape. Have anyone you know about these? Yeah. Internet opens to commercial use. SF lifts restrictions in 1991. There is an economics to it, or relation we spoke about in the structure. When we scale up, other departments get involved. Explosion of apps came out, instant messaging, UTP share, e-commerce, million of hosts, now a billion of users, internet goes very mainstream. And not where we are now, from 2005 to where we are now, it's being present. So internet is everywhere, broadband, 4G, 5G, Wi-Fi. We have rise of cloud computing, Google, AWS, and Microsoft, social media, smartphones, more mobile than fixed devices. And today, billion of devices, we have a billion of devices, and the internet is a critical infrastructure, not just a means of communication. So as a summary of chapter 1, I think we got a good introduction about networkings. We spoke about what the internet is and the overview of it. We also spoke about protocols, means of communication that we have as human beings, and devices as well. We spoke about network edges, access to networks, and the core of it. We spoke about packet switching versus circuit switching, internet structure. We talked about performance, whether it's and the four types of delays. We talked about throughput. We talked about layering and service models. We spoke a little bit about history and security, nothing in depth. So now you should have a context overview, vocabulary, feel of networking. More in depth and detail is coming along, especially with the application layer. I think we're going to have nice protocols to talk about and interesting things that are going to come up. And these are additional chapters, slides. There are only 2. So with the OSI model, basically the slide is saying the presentation session is really not related to network, and I said that before. It's mostly related to the application and the users, and the presentation allows application to interpret the meaning of data. It can be encryption, compression, machine-specific conventions, and sessions, synchronization, checkpointing, recovery of data exchange. So the internet stack is listed slide. These services are needed and must be implemented by the application. It starts always with the application and it makes its way down. So when we said in the first lecture, we're covering network from a top-down approach. So we gave an overview, chapter 1. We're going to dive into the application layer. A little bit about we have here about Wireshark is basically what Wireshark is. It has various tools. It can capture traffic for us, record live packets. Most of you have used Wireshark through the networks. It breaks down the traffic by layers. There's a filter and search on it where we can focus on specific packets or addresses or protocols. We can troubleshoot the issues, find errors, slowdowns, and drop packets. Detect suspicious activity, spot unusual connections or attacks. So the packet analyzer, we use PCAP. Basically, we have our application layer. So the user will use the browser, email, and it goes its way down, and we get to the link. It takes a copy of Ethernet frames that are sent and received, and then we will analyze them. So this is the idea of Wireshark. And we will have an assignment on Wireshark, but it will not be released now, because what I plan to do is I will make a manual guideline how to download Wireshark, explains a little bit about it, and I'll also install it in class, and we'll talk about it. Then the assignment will be released. And then from there, if you have any questions about the assignment, you can reach out to me, visit my office hours, or speak to the TAs, but it won't be anything too complex. So this is it, basically a wrap of chapter 1. If you guys have any questions, class is dismissed. You're good to go.
These slides are my sources.
Yeah, I uploaded them, and it's organized by week, so we're currently in week 2.
Question, how does this